Yeah, let me put it in slideshow. Okay, is that clear? Can you see it?
Yes.
Okay, great. All right, so the title is Zooming in on Brownian Motion with Einstein's Speed Demon, which is a mouthful. Unfortunately, we don't have a mouthful of pizza together, but I have to explain each topic, each word, and I will. Even though I'm sure you've heard about Brownian motion and you've heard about Einstein, you may not have heard about his speed demon because it's something that I invented. So it's not a common term, but I'll explain what I mean. But let me start out, since I love history and especially history of science, I always try to bring in a little bit of the historical perspective. So when we talk about Brownian motion, it's named after this person, Robert Brown, who was a botanist. And in 1827, he was using a microscope and observing grains of pollen, and he observed them jumping around, moving as if they were alive. And in fact, I think from what I understand, he thought that they might be, so he tried different things, and he always got that same result, that there was this constant motion, which then later on is referred to as Brownian motion. So that was in 1827, and maybe it's fair to say that although this was clearly observed, it was not understood. And it wasn't until 1905 that Albert Einstein came up with that explained Brownian motion. And his theory predicted a diffusion process. Diffusion is characterized by the mean squared displacement, or is proportional to time. So the square root of that, the displacement, the average displacement, is proportional to square root of time. And this constant d contains a lot of information, and in particular, it contains Avogadro's number. So this was considered very important step. This is one of his miracle papers from 1905. Well, that was his prediction. Up till that point, Brownian motion was observed, but not quantified. And no one had measured by tracking. What you have to do is have a microscope in space and in time where you could look at a particle and track its motion and actually measure to see if this relationship holds up. Well, that challenge was, maybe before that, if you were to follow one particle and zoom in, and I'm zooming in now in space, you would see a self-replicating pattern. It's self-similar. On every scale, you should see randomness. Now, this was, as usual, when there's a theoretical prediction, experimentalists try to rise to the challenge. And in this case, it was Jean-Baptiste Perrin who set up an experiment, again, with a microscope. In this case, though, he tracked particles and measured their displacement as a function of time. This was before computers, of course, so these were very tedious measurements, but he did them. And he confirmed Einstein's theory within his error bars. And for that work, he won the Nobel Prize in Physics, 1926. It was cited because of Brownian motion, the observation of diffusive Brownian motion, and also confirmation of the atomic basis for Brownian motion. Now, if I look at that equation, and I'm sure you've seen this before, a diffusion model, it looks innocent, but there's a problem with it. And the problem is that if you take this seriously and you say that x, if you take the square root of both sides of this equation, then you get that the displacement, the average displacement, is proportional to the square root of time. Well, we know that velocity is the derivative of displacement. So if you take the derivative of square root of t with respect to t, you get 1 over square root of t. The problem is that that diverges as t goes to 0. Well, what does that mean? That means you have infinite velocity of a Brownian particle. And so if the kinetic energy of a Brownian particle is 1/2 mv squared, that would imply infinite kinetic energy. This is obviously unphysical. And Einstein recognized that, not in 1905, but in 1907. And this is his paper. It's not nearly as widely cited as his 1905 paper. It was published in 1907. And what he realized is that the flaw was that a particle cannot instantaneously change its direction or velocity. And that's because it has inertia. And the inertia places a cutoff on a short enough time scale. What he predicted is that the motion should not be diffusive, but rather ballistic. Ballistic means that the displacement is proportional to t, not to square root of t. Now, of course, you could say that there is going to be a time scale where it'll be ballistic simply because it's not undergoing collisions. That typically is really impossible to see. I mean, for collisions in air, for example, that would be probably femtoseconds. Maybe it could be resolved, but there's a longer time scale, and I'll define that in a moment. But there's a characteristic time scale called tau sub p, which is known as the momentum relaxation time. And it has to do with how quickly can a particle change its direction and velocity. But what Einstein proposed was that there's this cutoff, and so at short enough times there should be ballistic motion. You should get a transition from diffusive to ballistic, and once you have ballistic, then velocity is a well-defined quantity, and therefore kinetic energy is well-defined. This was further developed by other theorists, most notably Uhlenbeck and Ornstein in 1930, so that's already over almost 100 years ago. Now, if you think about the timescales, they are a bit scary because let's take this concept of an instantaneous velocity of a Brownian particle. You just measure delta x and you measure delta t, and the velocity is delta x over delta t. And the claim was that as long as your time is short compared to this momentum relaxation time, you could see it. So let's take some numbers. So I'm going to assume not an atom, but we're going to take a little glass microsphere of silica, SiO2, at room temperature, 300 Kelvin. Let's take a diameter of 3 micrometer. What this would predict is a root mean square velocity of 0.4 millimeters per second. And if you want to measure that with some uncertainty, let's say 10%, you need a certain temporal resolution and spatial resolution. Well, in air, it's not so bad. It's 5 microseconds and 0.2 nanometers. But I'll say that now you might wonder, how could you measure a 3 micron diameter sphere to within 2 angstroms? And the answer is we're only asking what is the center of mass motion. So in principle, you could measure it to much, much better than the diameter of the bead, in this case, 2 angstroms. In water, it's much, much tougher. You need a time scale of 100 nanosecond resolution and 4 picometers. That's getting almost to the size of a nucleus. So, well, obviously Jean Perrin could not do that because he didn't have fast detectors. He didn't have computers. But until recently, this wasn't possible. Now, what would you expect to see if you could measure this instantaneous velocity? This was Einstein's very simple prediction. He said that if you could measure that, then what you would verify directly is the so-called energy equipartition theorem of statistical mechanics. And that is that in 1 degree of freedom, the average kinetic energy, 1/2 mv squared, is 1/2 kBT, where kb is the Boltzmann's constant and t is temperature in Kelvin. And then you would get, for example, if you put in the a 3 micron bead at 300 Kelvin, that's how you get this RMS velocity of 0.4 millimeters per second. Einstein, in his paper in 1907, went through that argument, but he concluded at the end that the velocity and direction of motion of the particle, this is translated from the German, so it sounds a bit awkward, will be already very greatly altered in the extraordinary short time theta, and indeed in a total irregular manner. It is therefore impossible to ascertain the average velocity by observation. So it's always fun when a theorist makes a prediction like that, saying that the experiment's impossible, because that gives us experimentalists something to do, right? But it did remain impossible until 2010. So for over 100 years, it remained impossible until we did it. So, but I'll get to that in a moment. Before I get to that, I want to jump from 1907 to 1970. This is maybe for those of you in the class, not for me and Coker, but for those of you, that seems like ancient history too. That's already over 50 years ago. But this man, Arthur Ashkin, known as Art Ashkin, invented something called the optical tweezer. How many of you have heard of that, by the way? Okay, I can't see all of you, but also feel free to interrupt me if you have any questions. Just speak up or raise your hand. This is informal talk, so feel free. He had this idea. I met him a few years ago. He sadly passed away, but he was 98 when he passed away. So he lived a long life. He spent his whole entire career at Bell Lab, which was a place where one could do research that was often curiosity driven. And for this work, he won the Nobel Prize in Physics in 2018. He was the oldest Nobel laureate at the time. And since then, we have our own John Goodenough from UT Austin beat him on that. But I think he won it when he was 98. So good news, it's never too late as long as you're alive, right? So anyway, Ashkin had this idea that you could trap particles with a focused laser beam. And it uses the fact that material is it's polarized. It is polarized by the electric field of the laser, and it's drawn into it. So it's attracted to the focus. That's why it's called a tweezer. And this is a picture showing a microscope objective to the left, and then you don't see anything, but you can see a glowing little microsphere. And it's a green laser, so that's why it glows in the green. This is probably done in water, if I would guess, because most optical tweezers are done in water simply because the index mismatch between water and glass is not, it's 1.33 compared to 1.5, whereas in air it's close to 1. So you have to worry about reflections more of the laser from the microsphere, but it can be done. So this is a beautiful picture, and many groups around the world use optical tweezers. Today, I would say most of them use it for biophysics or biology. So not very many groups study basic physics with it. And that was fun to come back to and address a basic physics phenomenon. This is a schematic of a typical setup for an optical tweezer. You have a laser beam shown there in pink, and you have a microscope objective, and you have a working distance, WD, which is typically very short, and that's where the particle like a microsphere will be trapped, and it will be stably trapped in 3 dimensions, and it will just sit there. Amazingly, the trap is deep enough that the particle will not be ejected by the thermal motion of the surrounding medium of, say, water. So it's a very deep trap, much deeper than 300 Kelvin if you measure it in Kelvin. It's probably a few thousand Kelvin deep, just because the particle size gives it a large polarizability. Now, we're interested in at least to begin with, we started in air, and in air, a single beam trap usually doesn't work. Sometimes you can make it work. So the setup is usually described in this way. You have two counter-propagating beams, which we can control, and we usually work in the near infrared at 1064 nanometers because glass is weakly absorbing there. And we use two lenses, and we focus the beams so they meet in the middle, and it requires very fine alignment. It's kind of like balancing two pins on their head against each other, but it can be done. And when we do that, we trap our atoms, or not our atoms, our microspheres. People have used tweezers to trap atoms as well, by the way. Now, the way you can see the motion when a little particle like a microsphere is trapped in air, the air is bouncing around and causing the bead to undergo Brownian motion. And the way you see that is because the little bead is like has an index of refraction, so it's like a lens, and the lens is moving around, and as it moves, it deflects the laser beam. And you can detect that on a device called a quadrant detector. I'll show you the picture in a moment. And you can also image it on the camera if you want to. But the actual measurements are done on the quadrant detector. And this is how it was done traditionally. A quadrant detector is something that is commercially available. It is a photodiode that is split into 4 quadrants. And the output gives you the ability to look at the sum or the difference. So you can, for example, you can call the 4 quadrants A, B, C, and D, and you can sum up the quadrants on one half, like on the left side, and subtract the ones on the right side. And the combined photocurrent will tell you if the laser beam is centered horizontally. As it moves horizontally, it will cause an imbalance in the photocurrent. So when you're on one side, you'll get predominantly a positive voltage. On the other side, you'll get a negative voltage. And you can do the same trick in the vertical direction. So by doing that, you can actually monitor the motion of a bead. But here's the catch. These quadrant detectors are rather slow. They typically have bandwidths around 100 kilohertz. You might wonder why, and it's just because of their size, because they have a large surface area, so they have a large capacitance, and you know about RC constants, so they have a large RC constant, and therefore they're inherently slow. And I heard a talk about this in roughly 2008, I think, early 2008, in E.L. Florin's group, who's a biophysicist in our department. And he was talking about the Brownian motion, and they were trying to see this effect, but they couldn't, because they were using a standard quadrant detector. And I remember during this talk, I was sketching out a way that I thought we could speed this up. And it was a simple idea, actually, to separate the functions of splitting the wavefront and photo detection. And so after his talk, I showed EL the sketch, and we decided we're going to work on this. And I had an undergraduate, Isaac Chavez, who's now a staff member at Lawrence Livermore National Lab. This was years ago. And he built it. It was complicated. It used optical fiber bundles, and we fed them into fast photo detectors. But immediately, we got a factor of 1,000 speed up in detection. We could go from 100 kilohertz to 100 megahertz. So that was, now we're starting to cook with gas, right? Because now we can replace that old slow quadrant detector with something much, much faster, which we did. And when we did that, we were able to see the following. This is the mean squared displacement in nanometers squared on the vertical axis. And on the horizontal axis is time. It's a log-log scale. And what you see is the results of measurements. The red squares are done roughly at atmospheric pressure. The circles are done at, we had the ability to pump out some of the air so we could go to vacuum to lower pressures. And so we repeated these measurements at lower pressures. And then the noise floor is shown with the triangles. You can see that our measurements are, first of all, the slope is 1. And that is characteristic of ballistic motion. That contrasts very much with the diffusion model, which is shown in the dashed lines. The red dashed lines and the black one show a smaller slope, half the slope, because that's diffusion. But we clearly could see ballistic motion. Now you might ask, where's diffusion in this picture? And the answer is that because our particles are not free, diffusion shuts off because the particles are trapped, and so they can't wander very far away. But what we see is that there's a very clear regime where the answer doesn't depend on whether or what the pressure of the gas is. We just see ballistic motion. And this is on a linear scale. You can see the mean square displacement is quadratic in time. It's a parabola. And you can see that for the size of the bead, we calculate a momentum relaxation time of about close to 50 microseconds. And that will change at different pressures. So it's 50 microseconds at atmospheric pressure, and it gets much longer as you go. It gets to 147 microseconds at lower pressures. And you can see that the theoretical prediction is the dot dash blue line, and the experiments are shown in red and black, and they agree very well for timescales, say, shorter than about 15 microseconds, well under the momentum relaxation time. And this is what actually we record. We record just the actual displacement is shown here at, again, different pressures, and just focus on the red because that's atmospheric pressure. And we then can convert that into a velocity. And this was really the first direct measurement of the instantaneous velocity of a Brownian particle. Now, the question is, how does it compare with the prediction of the equipartition theorem? And the answer is no adjustable parameters. This is what we saw. We see a Gaussian distribution, the so-called Maxwell-Boltzmann distribution, with no adjustable parameters, using the quoted value for the mass within the uncertainty of the mass. We see excellent agreement between theory and experiment. And interestingly, the bead has the same kinetic energy as a single air molecule, because that's just the statement of the equipartition theorem, that average kinetic energy is 1/2 kT. And that's what we measure. So this was the first direct test of energy equipartition for Brownian motion. We published this in 2010, measurement of the Brownian, the instantaneous velocity of a Brownian particle, published in Science. It's actually had about almost 700 citations since then. So it's gotten a lot of attention, and it was an important, I think it was an important milestone, mainly because now we could verify equilibrium phenomena, and then we could go out of equilibrium. And as I'll explain, maybe that's where the real frontier is, non-equilibrium. But if you can't get the equilibrium part right, then no one's going to believe you about the non-equilibrium. So it was very essential that we did this.
Dr. Eisen, could you clarify how you went? Could you clarify how you went from the mean displacement to the instantaneous velocity?
Yes, we took this record. So the upper left corner, you see just a record of displacement in time, and we had that calibrated, so we knew what it corresponded to. So we had position as a function of time, and so we just numerically calculated the velocity from that. Now,
Okay.
you notice that the signal to noise is worse. So we do pay a little bit of a price in going from, so we're not measuring velocity directly, we're measuring position, but we
Okay.
can turn that into a velocity measurement and the error bars in the end. I have to say that we took a lot of data to reduce these error bars. That what I show you here was one experimental trace, but we actually would accumulate billions of data sets to do this, which didn't take all that long because we had a very high bandwidth of detection. Okay, so this is great. This is, important step. I've called this, although it hasn't been adopted by the community, I call this Einstein speed demon, just because I like it. But it's a kind of reminiscent of Maxwell's demon in the sense that you can know what the particle is doing. It's a single particle. It's not an ensemble, but nevertheless, the point is that we can measure it on very fast time scales. So I call it a speed demon. Anyway, and we were very excited. And then we got this anonymous referee who said, even though it did get published, he said, that's nice, but Einstein said it's impossible to observe instantaneous velocity in a liquid, and Raisin's group only did it in air. Okay, well, they had a point. It seemed a bit snarky, but what can I say? So anyway, you sort of have to go back to the drawing board a little bit and realize that what we constructed is a microscope in space and in time. And essentially what we're doing is just, if you go from Brown, Robert Brown's work with a microscope, he observed it in space and in time, but with only the resolution of his eyes. Then Jean Perrin used a microscope and the resolution of a stopwatch. People used the resolution of a quadrant detector, but now we've gone 1,000 times faster. So we've pushed the limits of this microscope, but now we have to push it even farther, because if we want to go to water, and I'm just showing these same numbers again, just to remind you, we have to get much better resolution, both in space and in time. And this seemed daunting at first, but we looked at the numbers and we realized that it's a combination of things. We could we could improve our situation by choosing a higher density material. So we went from silica, which is basically glass, to barium titanate, which has higher density and higher index of refraction. We also alternated between water and acetone. Acetone has a much lower viscosity, somewhat lower density. And 4 years later, we did the experiment in liquids, also published in Science. And I would just say to this to the anonymous referee. Unfortunately, I can't tell it to his face or her face, but it felt good. So we were able to see this now in both air and in liquids. I would say that we're pushing the limits of detection now, because in this experiment we were at the quantum noise limit of the laser. In fact, the detectors that we used were the same design as used by LIGO, the gravitational wave detector collaboration, and so we were limited by the shot noise, the quantum noise of the laser. And you really can't. Well, you can do better under certain cases with squeeze light, but we're not going there yet. But this was pushing the kind of the ultimate sensitivity of our method. And you might wonder, can we do better? And at the end of my talk, I'll show you how we're going to go 1,000 times better. So we're not running out of steam yet, but we have to figure out a smarter way to do it. This microscope in space and time is going to get 1,000 times better than that, and that's not the end either. But let me continue. We did a very exhaustive study to test the equipartition theorem in a liquid, and again, within our uncertainty, very good agreement. This was published in 2015. It was almost disappointing for me. I mean, I had hoped that we might see some deviation, like maybe in the wings of the distribution. Nothing. It's just perfect, right? So you could say wow, that was a lot of effort, and did you really learn anything? But I think we now we have a system where we can really probe fundamental questions, and let me get to those now. First of all, I would say a lot of the interest will deal with hydrodynamics. So it's the combination of Brownian motion and hydrodynamics. And when we think about the origin of gas kinetic theory as actually developed by Maxwell, we think about molecular dynamics, where you have a particle like a microsphere and you get particle collisions. You can have a temperature associated with that, and Stokes drag, which is just a phenomenological number. In hydrodynamics, though, something more complicated happens. And that's been predicted for a long time, but not observed, is that there's a bare mass, that is the mass of the bead itself, but as it moves, it drags along with it some of the liquid. And that is known as the added mass effect. And M star is bigger than M. In fact, it's been predicted exactly what it should be. It relates to the mass of the displaced liquid. So in air, that mass is negligible because the density of air is so small. But in liquid like water, it's substantial. There's also memory effects, which make it much more interesting. Now, what that does is it modifies the Maxwell-Boltzmann distribution. So everywhere where you see mass, you really must insert M star. Maybe I already showed that. No, I don't know if I put M star here, but when we fit it, we actually were fitting to this added mass, and you get a modified energy equipartition theorem, not with the bare mass of the particle, but with this added mass. And this is something I've been discussing with a brilliant theorist from Rome, Massimiliano Giona. We've established a collaboration with him and his group. And he makes a convincing argument why this would be a violation of energy equipartition. It really, in a way, forces somewhat of a crisis in statistical mechanics, because it's one or the other. You either believe equipartition or you believe this hydrodynamic effect. However, why we can't claim that yet? The reason being that there's uncertainties in the microsphere density and the radius. So radius is something that we can see pretty clearly because we have a good microscope. We can measure, I would say, we can measure the radius to a few percent. But the density is much less known, and we have some indications that the process of making these microspheres it causes some porosity of the glass. So it's actually porous glass, and the manufacturer does not really provide any details on this, and they can't weigh it because you can't put a micron-sized bead on a scale. There's no scale that is sensitive enough for that, except I'll show you a scale in a moment. So that's why we couldn't really claim this yet. I'm going to take a little segue on something else that we did before I'll come back to this hydrodynamics and this added mass question. When after we did this work in 2010, we were still thinking about doing things in air, and my student Tongkang Lee, who's now a full professor, or he's about to be promoted to full professor at Purdue University, doing brilliant work on his own. He said, let's trap it in vacuum, and let's see if we can cool the center of mass motion towards the ground motional state. So that was an interesting challenge, and Tongkang really led that effort. What we did is we used our dual beam tweezer, and we applied feedback cooling, so we could monitor its motion not just in one dimension, but we actually did this in 3 dimensions. And when we saw the bead moving in one direction one way, we would give it an optical kick to counteract that motion. And doing that, we were able to suppress the thermal motion depending on the pressure. So the best result that we got was at very small pressure, millipascal, 5 millipascal. Still not ultra high vacuum, but it didn't seem to matter. We got to a temperature of 1.5 millikelvin in the center of mass motion. But that's kind of striking because the internal temperature of the bead, as best as we could tell, was still 300 Kelvin. But the center of mass was cooled down. Now, this is not yet the ground state, unfortunately. But since our work, I think we started this work in 2011, and it was the first realization of laser cooling of a levitated macroscopic object. This was published in Nature Physics in 2011. And I didn't continue this work in my group. Hong Kong is now doing continuing work like this at Purdue. But meanwhile, 2 other groups were actually just a year or 2 ago were able to do in a similar system. They were able to cool the center of mass motion to the quantum ground state. And this was 2 landmark experiments published in Science and Nature. So I was very happy to see that. Their goal is to ultimately to make quantum superposition like Schrödinger cat state of a bead being in 2 locations and to study fundamental decoherence. As an aside, I had this is not something I'm doing yet, but we're building a collaboration with a group in Europe to make ultra large Bose-Einstein condensates to test general relativity and quantum mechanics together. So this is a new project which will take us, if we get funded by this, will take us back to some fundamental physics. It's interesting, people have tried to quantize gravity, but experimental tests are very difficult. This experiment actually would test gravitizing quantum mechanics. But the theorist behind this is Roger Penrose, who won the Nobel Prize just a few years ago, or I think in 2020. And he's very interested in this kind of test of fundamental decoherence due to general relativity. So as an aside, but we'll come back to that. Then we went on to do other work on Brownian motion. We studied boundary effects. I won't go into the details too much because it's kind of technical, but I just wanted to mention that there's other interesting problems where we put a boundary and we could move the bead close to the boundary and see some substantial effects due to the boundary in a liquid. And so that work was done and finished, and the students graduated and we moved on. Now, let me come back to this picture. I showed this picture this was the short time Brownian motion in air. Now that we've established the equipartition works for a Brownian particle, we can use it and turn it around because the relationship is so simple. It's 1/2 mv squared equals 1/2 kt. Well, kb is a constant, so we measure the velocity. So you can do one of 2 things. You could, if you know the temperature, you could use this to measure mass. Or if you know the mass, you could use this as a thermometer. In other words, you could use the temperature or mass as a fitting parameter for this curve. Of course, in the cases that we've done so far, it's not changing. Mass and temperature are not changing in time. So it's not that interesting. But what happens if they do change? Then having a local thermometer or a local mass measurement is critical. And 2 interesting cases that we're going to pursue in the future. One of them is what's called heterogeneous nucleation, which the application is ice nucleation and cloud seeding. I've showed a nice picture of a cloud, but process is not really well understood. But with our trap bead, we could expose it to saturated air at low temperature and observe the change in mass as it starts to nucleate ice. And by measuring the equipartition theorem, we could actually monitor the change in mass in that way. If the mass is not changing, but what if the temperature is changing? And when my student Logan Hilberry has been working on inducing convection turbulence with a heated a wire, and in convection there will be vorticity and also temperature variation. And having a local thermometer that can also measure vorticity will allow us to probe turbulence, and maybe in a way that hasn't been done before. For example, there's a prediction by Kolmogorov about the smallest scale of turbulence. So we can address that. And so it's very interesting to think of these things. And I said that, I kind of was teasing you that we couldn't take a micron size bead and put it on a scale, because there's no scale that will do it except for our optical tweezer. And that's what we did. So we reported this work in 2020, weighing an optically trapped microsphere in thermal equilibrium in air. Logan is the first author. And actually, we find that we can actually determine in a very short time, we can determine the mass of the bead to about 1%, and much faster than any other method that we know of. What else can we do? Well, what we're working on right now is, so everything I'm talking about now is non-equilibrium phenomena. Turbulence, ice nucleation. What about acoustics? Well, that's a non-equilibrium phenomena. You can have acoustic signals in air or in water or liquid. What we learned from all of this is that because we can monitor our bead on a very fast timescale, and the bead has very low inertia, we can subtract out the Brownian motion, because for short times there is no Brownian motion. It's ballistic, and if we measure that ballistic velocity, then we know everything about it. So that's why it's a speed dim, and we can have that knowledge, and therefore we could be very, very sensitive to an acoustic signal. For example, I'm in discussions with a group that is searching for dark matter in a bubble chamber. This is at the Snow Lab. It's called the PICO collaboration at Snow Lab in Ontario, Canada, deep in a mine. And they would like to do acoustic detection of dark matter, or it could be also neutrinos, cosmogenic neutrinos. This is interesting to me, going back to my early days in particle physics. They were using just a commercially available microphone, which is very insensitive. We think that, well, we're not going to put an optical tweezer in a bubble chamber, but I have another student, Yi Shu, is working on integrating a very thin membrane made out of graphene to repeat the same short time Brownian motion, because we can integrate that in an optical fiber interferometer, and that could be very compact. You could actually put it inside a bubble chamber, and so having an array of ultra sensitive acoustic detectors could be very interesting. There's other potential applications, even in medicine, potentially to image the stopping of high energy protons in proton cancer therapy. So we're working on this. Some of the future directions, I'm going to wind up in a few minutes. I don't want to go on too long. So I've told you about short time Brownian motion. What about ultra short? Well, you have to be careful with that word these days, because for people like Mike Downer or Todd Dittmeyer or Heglish, that means femtoseconds. Nowadays, people are even reaching attoseconds. But for us, we like to make a step from nanoseconds to picoseconds. And what we will do, and we actually have in the lab a picosecond laser ready to go. With that, we will be able to actually test the added mass prediction in a very clear way. We can also study non-equilibrium dynamics in the onset of irreversibility, so-called arrow of time, to really understand viscosity from first principles. This is the way we would do this is, I don't want to get bogged down in the details, but I just wanted to point out that when you, with a CW laser, which is what we used up till now, we were getting our time resolution by the bandwidth of the detector. But But once you've reached the shot noise limit, you can't put more power on the detector because it will be destroyed. So we've run out of resolution there. And the way to get around that is to switch from a CW laser to a pulse laser, because then you're concentrating all the photons into a very narrow window in time. And you're getting the time resolution not by the bandwidth of your detector, but rather by an optical delay path. So we send a pulse, the first pulse shown in a big red pulse. We then split into two pulses, one which we send on a different path with a delay time tau 0, and we recombine them on a second polarizing beam splitter, and then we focus them both. And by doing that and then separating them by polarization, we can actually measure the response time. We can do this just to see, and then by varying, we can vary the delay time from less than 1 nanosecond to several nanoseconds. We can go in principle down to 100 picoseconds, I think, where this where we should recover the bare mass. This added mass effect should go away, and then we will see how the bead acquires this added mass in time. So that would be really the purpose of that experiment. We can also do a pump probe detection where we not only get the time resolution, but we actually give the bead a kick. So we give it a strong kicking pulse, shown here in the transverse direction. And we know what's going to happen. The bead will get kicked, but then it's going to its motion will be damped out. What I've predicted is a classical Zeno effect. We actually did the first quantum Zeno effect with atoms about 20 years ago, but now we want to revisit this with a very classical particle to see whether when does viscosity turn on? You know, you think about viscosity as just being an inherent property of a liquid, just like you think of Ohm's law as being a property of a conductor. But Ohm's law and viscosity are only bulk quantities. They are not microscopic. And just like Ohm's law, if you could really look at a single electron, you would see that Ohm's law doesn't turn on immediately. But we don't know how to image an electron that way, but we can image a little bead of glass. And so we should be able to see the onset of viscosity. And that's very important because viscosity is put in by hand in the Navier-Stokes equation. It's not a fundamental quantity. So understanding this has always been a puzzle. We can maybe even think about exotic things like moving a bead with no viscosity at all. So it's kind of interesting to think about. I don't have time to talk about everything else I'm doing. Part of my effort, as I said, is split with medicine, and I have a big program of isotopes in medicine. I'm also the founder and chairman of the board of the nonprofit Pointsman Foundation. If you're interested, you could listen to my colloquium, which I gave on April 6th, just a few weeks ago, and it's posted on YouTube. You might be interested in hearing that. And I'm going to be recruiting new members to the group, something I, in the past, didn't often do because the group was always very full. But because of the pandemic and other things, a lot of students graduated. I'm rebuilding efforts in the Brownian motion on the medical side. And if we get funded on this BEC experiment, we'll be rebuilding that, at least some effort in ultra cold atoms. I don't know yet whether that's going to be funded. So that's what we're doing. And I give you a kind of a taste of some of the things we're doing. And I'll end here and thank you for your attention. And I'm open for questions.
So I was kind of curious from a practical standpoint how the microspheres are created, or what I mean,